Hello and welcome to our presentation. My name is Iván Solt and I am the product manager in a team that is, among others, responsible for the development of chemical structure, curation, and normalization tools. This will be a joint presentation held by myself and Ákos Tarcsay, the product manager of calculators and discovery tools. In the first half, I will give you a brief introduction to the principal concepts behind our structure normalization tools, and then I will hand it over to Ákos, who will be focusing much more on an application context. You all know how chemical structures can come in various shapes and forms depending on the source of the data. The variability of the representation can depend on a number of factors: business rules of the providing partner, individual differences between chemists who create the data, technical and even file format limitations, flaws in the process that was used to create the files, just as well as a human error. It can also happen that the data set was prepared with one purpose in mind and will later be used for something different, but the requirements will also change. If you look at this tiny collection of chemical structures, you will notice ever so small details distinguishing them from each other. Some have the same functional groups drawn differently. Others might just be the two tautomeric forms of the same compound. Some are delivered in their salt form or contain properties that might only increase the noise in your data set. Some of them contain basically just plain errors. It has been well known how the normalization of compounds is critical for reliable chemical searching. As the data that needs to be unified and handled can come from a number of different sources, it is critical to have certain aspects of the chemical structures canonicalized. Aromatization, tautomerization, or the consistent representation of functional groups are good examples for this. However, in order to ensure that the correct chemical structures are converted into a normalized representation, typically a curation step precedes the structure normalization, or to be more precise, these two go hand in hand before a chemical structure gets, for instance, registered into a database. And it is, of course, very important that the query structures undergo the same normalization as the database content to ensure consistency during the search. However, the chemical search is not the only context where the correctness and consistency of chemical structure information can influence the outcome significantly. As Ákos will show you in a few minutes, in the case of building and the application of chemical and physical chemical predictive models, the accuracy and reliability of the results can also be a victim to poorly represented chemical structures. Structure curation is taken care of by Structure Checker. The main goal of this tool is to identify errors or unwanted patterns in the data set and either fix these automatically or at least filter out the structures that contain problematic details. There are a number of uses of Structure Checker, but for the sake of simplicity, let's focus on two basic scenarios. In the cases where the identified issues are difficult to fix automatically or are not necessarily errors, but the chemists want to be aware of them, a simple checking workflow can be applied. In this simple workflow, the problematic and problem-free structures can be separated or at least flagged according to their nature and then processed further. In other cases where the process requires the elimination of issues, a more complex workflow can be thought of. However, even in this case, some errors might not be handled automatically, and the chemist's intervention might be needed. Some issues are easy to fix, such as the removal of unwanted properties, for instance, query properties or atom maps, or even the conversion of known aliases is straightforward, but others can be more challenging, like valence errors, for instance. Although Structure Checker can identify and fix a large number of issues out of the box, completely custom rules can also be defined. The configuration of the checking protocol uses so-called checkers that identify the problematic parts of the molecules and corresponding fixers that aim at eliminating the errors. These checker-fixer pairs can be configured to serve a curation process. They can be essentially fused together in a sequence of checking steps to find all problematic patterns in your data set. The configuration itself can be stored and used in an XML format or the configuration string, as Ákos will show you in their application. The structure normalization step carried out by Standardizer expects that some fundamental errors are already eliminated. Standardizer will, for instance, not handle valence problems in your dataset. It will, however, convert your chemical structures into a canonical representation in a fully automated fashion. Unlike in the case of structure checker, users will not have the opportunity to intervene with the process on the fly. Standardizer focuses on modifications that are unambiguous and transparent. Finding the canonical tautomeric form of compounds, the removal of salts and solvents, normalization of how certain functional groups are represented are very common tasks of the standardization step. You already sense how these modifications carried out by structure checker or standardizer might influence the calculation of certain descriptors, such as molecular weight, hydrogen bond donors and acceptors, or physical chemical properties. But Ákos will share the juicy details very soon. Just like structure checker, standardizer is also configured with individual modification rules called actions. These actions are fused together, similar to the case of structure checker, and from a technical perspective, the configuration resembles that of the other tool. And just like for structure checker, custom actions can be prepared here too. Despite the many similarities and even overlapping functionalities, these tools fulfill two rather different roles in the normalization workflow. While structure checker is a semi-automated creation tool that typically requires user interaction, standardizer is a much more integrated and automated, if you like, more invisible building block of the process. And at this point, I'm handing over the presentation to Ákos.
Welcome everyone, my name is Ákos Tarcsay and I am the product manager of calculators and discovery tools. And let me continue this presentation with applications of structure checking and standardization on building predictive models. We introduced a trainer engine that automatizes the translation of observations into predictions and includes all the necessary steps for building the model, analyzing the results and validating the models to be able to select the best performant prediction that is to be used in a production manner. If we investigate deeper the model building itself, first the input data is to be pre-processed. That has two different domains. One is the observation, which are classes or values. That is currently out of the domain of the trainer engine. But chemical data pre-processing is a special challenge, since chemical structures can contain various errors, different drawing representations that calls for standardization actions to be able to have the consistent representation and to reduce the variance and noise in the database before generating the descriptors, submitting with the hyperparameters for the trainer engine itself, and then validating the results and with loops optimizing the descriptors and optimizing the hyperparameters. This chemical data cleaning and standardization popped up as one of the most important missing features from the trainer engine. And therefore, this is our latest development. We integrated the standardizer functionality into the trainer engine in a way that is taken into account while descriptor generation that influences both the training and the prediction. So when you are training your model and validating the model, you can enjoy the impact of standardization. So differently drawn chemical moieties can be turned into a consistent representation. Or if your observations are taken under conditions that are selecting the most abundant tautomeric form, then the standardizer can take care of this transformation as well and reduce this variance coming from the chemical representation itself, since this virtual representation is not obviously what is in your test tube, but is under your experimental conditions. But standardizer offers you a technology to be able to move your chemical representation as close as possible to the experimental conditions and the different input structures can be consistently treated in your model building and in your prediction. So by implementing the standardizer, both at training and at prediction, the very same rules will be applied. First, let's have a look at the data itself and the chemical data pre-processing via some structure checker examples. One of our oldest example is a HERG cardiotoxicity endpoint from 2010, what was submitted for structure checking, and we found 10% issues among the cases with the highest propensity of radicals. But first, one of the examples were checked back in the original reference, and the triazole ring is connected to a sulfur in the Marcus representation of this publication, and in the supplementary data of this dataset, the SMICE strings were given, and in the SMICE string, the sulfur was represented with a lowercase letter, which is an aromatic form of the sulfur atom. Probably this was a mistake. The other is the radicals. How can this large number of radicals be present in such a dataset, and whether these are real radicals? And one of the examples is amiodarone, which is not a radical, but the nitrogen was shown with an N plus in brackets with 3 connections. That in the SMICE terminology resembles a pentavalent nitrogen, a nitrogen with 5 valencies, and therefore the missing valence, which is not given in the SMICE, is automatically turned into a radical. The correct representation for a protonated tertiary nitrogen should include a proton atom as well in the bracket. So this type of nitrogens popped up in this dataset, and these were in the IO module turned into radicals, which were obviously not radicals in the original dataset. We looked at Campbell for penetration data as well, CACO2 penetration, where no structure checker issues were found, but what could influence the model building and that popped up is the multi-component structures and one real element. Altogether, 4% of the data contained these issues. A larger dataset, an HTS campaign result, is published in PubChem bioassay, where close to 4% of the datasets had multi-components, as it can be in real life in a HTS dataset, but we also found rare elements and solvents in this dataset. And altogether, 4% is to be somehow standardized or turned into a consistent representation. And the last example of the input dataset is METLIN, Small Molecule Retention Time Dataset, SMRT, that was published recently for machine building for analytical use case. And in this large dataset, we also found 6% of cases with issues, including again valence errors, rare elements, and some query atom properties. So from old datasets to most recent datasets that are coming from external sources, you can expect still to have 4 up to 10% issues that are to be pre-processed, filtered, or fixed before even starting your model building and your training. And next, I want to move to Standardizer, which offers you tools to have a consistent representation and to mimic the experimental conditions, the structures that are observed under your experimental conditions. One extreme example is imipramine pamoate, where a complex salt is given in this chemical entity, although the active pharmaceutical ingredient is only one of these 3 molecules. And if you are calculating the molecular weight for this complex, it will be different from the one that is forming an interaction or where you want to study pK or any of the properties. The other example is Tautomerization, and here I'm showing you furan 2-ol, which has an enol-oxo tautomerization, and therefore it can be even in a registration system in two different forms, or in an external or combining external and internal source. This can be drawn differently, although the associated observed data could be the very same. These two tautomeric pairs will have different polar surface area, hydrogen bond donor or acceptor count. It influences the fingerprints that are calculated, log P, log D values. Therefore, the descriptor itself will be different for the one molecule that is observed and experimentally studied. In the SMRT dataset, we run the standardizer and calculated the log P values before and after the standardization step, and I'm showing you those cases where there was a difference in between the calculated log P. There is a nice linear correlation with R square of 0.836, although only this tiny transformation to turn the molecules into the ChemAxon Tautomer isomer models most frequent or most abundant tautomeric form influenced the log P quite significantly. And this will be propagated in your model building as a variation of the descriptors themselves. Log P calculation offers an option to only take the major microspecies into consideration, but this is an example how much influence of the calculated properties could be achieved by a standardization of your dataset. So let's move to real examples of building models. And first, when I started to work with the SMRT dataset and built a classification model, I used Data Inspector with filtering to false positive assessment and recognized the pattern in these molecules that were not correctly predicted, where the nitro group is differently drawn on different molecules. And when I investigated all the compounds having nitro groups, I recognized that the majority, 88%, had charge separation and correct representation, but 12% of the cases had missing charges, and therefore these were filled with hydrogen atoms, which is most probably an error in this dataset. So I decided to use this as an extreme example and training on correct type 1 molecules, random 6,000 molecules, and use this erratic type 2 as a test set to be able to assess the effect of this drawing inconsistency in the two datasets. I run two model buildings, one with and another without standardization, using the standardizer rule. And I am showing you the model configuration in the trainer engine, where we used 28 descriptors for the retention time, activity value, and we are building regression random forest models. The other configuration included this standardizer action that translated the wrongly represented nitro group into the charge separated correct representation. But that was the only difference in between the two models. And here you can see the results. The predicted and the observed values are plotted on the first chart. The purple symbols are the test sets with standardization, while the red dots are without standardization. As you can see, there is a better fit for the standardized case. The delta versus the observed values shows that the purple is scattered around 0, while the red has a correlation with the observed values. No high values were predicted in this set. And the Pearson and the R square values shows a clear separation, where the standardized set had much higher accuracy. Also, in case of classification that is less sensitive, or that can be less sensitive to variations of the descriptors, I'm showing you the test set results with regards to false positive ratio and true positive ratio, that is the ROC curve, and the standardized model building had higher area under the curve, and by investigating the classification metrics, higher Matthews correlation coefficient, sensitivity, and global accuracy could be achieved with standardization included model building. The second example is Tautomerization, where in the SMRT dataset, 7,000 cases were selected with single Tautomer, and 252 cases where Tautomerization affected the molecules were used as a test set. And again, we run it with or without standardization with this simple rule. To be able to show you the tautomeric effect, now I am showing side by side the predicted versus observed values for these two datasets, and the non-standardized is shown with red dots again, and purple dots are showing the standardized case. As you can see, more molecules with higher error can be observed in the non-standardized set, and the Pearson and R-square values again shows quite a bit of a difference with only this single line change in the configuration that influences the standardization. But Tautomerization is a double-edged sword, since this is included both in the training and in the prediction, which means that we are losing one kind of a resolution, since the model will be consistent even though different tautomeric pairs are submitted. If this standardizer action is set, the descriptors will be the very same for the different tautomeric pairs. So you will not be able to model differences for your tautomeric pairs. So if you have a data set where tautomeric equilibrium is measured, this is obviously not to be used. Or if you have experimental conditions where different forms of the molecules can be studied, then Tautomerization will hide these effects. But other cases like multiple fragments, salts and solvates, which does not influence the observed value, the experimental value, Standardizer is to be used for consistent representation and for consistent results of your models. And I'm showing you this via Playground interface. The trainer engine offers integration by selecting the production flag, or by setting the production flag. The models are immediately made available in the Playground interface for single molecule calculations, and the upper widget is showing the prediction using the standardization included model that had the tautomerization, and the non-standardized one. Predicted values, conformal prediction errors, and most similar structures are shown and graphically represented. I selected a very simple use case with the most simple tautomeric pair and oxoanol tautomerization to demonstrate that the standardized case had the very same predicted value, same error, and the very same most similar structures as an applicability domain, while in the case of the non-standardized model building, we ended up with different predictions, different errors, and different most similar structures. So if this is the same molecule under your experimental conditions, then you should select the first of these pairs, which will result in the same predicted values. So in summary, we went through examples from external sources where using structure checker in the pre-processing as an offline step can help you filtering out noise and increasing the accuracy and correctness of your input dataset. And I showed you the importance of standardization on the descriptor generation and the accuracy of model building. With that, I want to thank you for your attention.